Welcome back to the Unsupervised Learning Lecture. We were about to discuss the density-based clustering algorithms. I will start with HBScan. That is a quite old algorithm, but still one of the most popular and well-known density-based clustering algorithms. This HBScan essentially means density-based spatial clustering with application with noise. So as you can already see from the name of this method, noise is a very important element, and this is what it does. It is able to detect noise. So let's see how this algorithm works and how it succeeds with noise detection. First of all, let's have a description of what density-based algorithms are. What are the basic assumptions? What you can see is a very typical example that you can find to explain how density-based algorithms are characterized. The idea is that you have regions of high density points, and those regions of high density points are your clusters. And the high density points regions are separated among each other by a sea of noise. So the idea is that you have islands, and those islands are the clusters, and you have a sea, and sea is the noise. You can decrease or increase your noise level depending on how severe and robust is your noise detection, and depending on how you detect your noise with your algorithm, on the parameters you select, you might find different clustering, as you can see in this very simple sketch on screen. So if you have high level of C, so if you're detecting most of the noise, you have just two clusters, rather small also. If then you decrease the C level, you're gonna find new clusters, and then you're gonna find also the clusters somehow larger. And this is the assumption. So you have, the idea is still the following. So you have peaks, very dense. Those are the centers of the clusters. And then you have all regions around those peaks which are much less dense. This is the concept. So now let's see how we can find the sea, and how can we find the islands which are our clusters. We will come back again with a sketch, as before, a two-dimensional example, where we can see how this algorithm works. The basic idea of HBScan is that there are some core samples, and the core samples constitute the core, the basis of clusters. If there's no it is not possible to define a cluster if there's not any core points inside the cluster. So let's see how we can define these core points. We use two different parameters. One is a distance, that is epsilon, and the other is a minimum number of points. In this example, we set equals to 2. As you can see, we have drawn, we can see on the screen some spheres around our points, spheres of circles, considering that we are in two dimensions, with radius epsilon. And these spheres are the distance outside our samples, and we are interested to see whether within this distance a point has at least n mean other points. If this happens, that point is going to be classified as a core point. So in this case, we can find 4 core points, which are the particles that are colored with red. Starting from these core points, the red particles, the red points, starting from these points here, we construct our clusters, and the clusters are composed of all those core points that are interconnected, so which means that are at least at a epsilon distance from each other. plus all the other neighbor points, which not necessarily must be a core point. So we can see to the right cluster that we have these three core points that are interconnected neighbors, plus two other neighbor particles which are not core points but still belong to the cluster. Also we can see another cluster to the left with only one core point, plus we have two other separated distinct points which are not close to any cluster, so those are labeled as noise. So this is our final result. We find two clusters and 2 points that are labeled as noise. So the concept is rather simple, and let's see how this algorithm performs. We come back on the dataset that we have seen already before, that is constituted by our 6 clusters plus a sea of very dilute noise. And then in this case we apply our HBScan algorithm as described before with the parameters that we can see here. And it actually, we can see that it works. We fixed at least 10 points as a minimum number of samples for the core samples of neighbors for the core points, and the radius epsilon is equal to 0.8. We can detect the 6 clusters comprise the half moons, and we are able to isolate noise. So please be aware that in this sample here and the next plots of clustering applied on noisy data, I will always remove the noise. So noise is simply not, is labeled and then is not plotted to make more to make it like the plots more understandable. Again, if you're interested in this discussion, would like to see to change the plots and having plots with the noise, you can go to the AI toolkit. As you can see now, this works, so I would say we are quite satisfied with this result. But there's a number of problems about this algorithm. So maybe one is already quite clear to you. And the most evident problem, I would say, is the fact that we have used 2 parameters. So we have epsilon and the minimum number of samples and mean in this case. This can be a problem because from having only one parameter, as we did before, for example with k-means or the distance in agglomerative clustering, to having 2 parameters, having 2 parameters is much worse actually. The reason is that you might want to apply your clustering algorithm to very large data sets. So in this case, you might have to iterate many times your clustering, and this can be time consuming, and doing the exploration for 2 parameters is much more complex than with only one. And another problem is that it's not only like the fact of having 2 parameters, because okay, you have one more, but the fact that there is one parameter, epsilon, that is very difficult to understand, or at least to guess in advance. While we had before the number of clusters, for example, and that could be somehow, it is more understandable. This epsilon is very, very difficult. While n-mean is somehow, we can represent it as, we can imagine this as the minimum number of points that we wish to see in the smallest possible cluster, because if one core sample must be neighbored with at least 10 points, we might imagine that the smaller cluster here has at least 11 points. This is one problem, okay, but there is another problem that is somehow more severe, but maybe less evident. And the point is that when we fix these 2 parameters, epsilon and n-mean, we are essentially fixing the threshold that we are the sea level, let's say, as in the example before. We are fixing the density of clusters that we aim to see. So in this case we have 6 clusters, but they all are somehow similar density, so they are all quite dense, and this is fine, so it works quite well here, this algorithm. But imagine if we had another situation. So now look again at the data set to the left, and instead of having this data set, we might have a different situation as this one. So here we have essentially another small cluster to the top left. Well, at least you can see it, I would say. I know it because this is can be generated. I have generated using the same function as for the other 4 blobs, the rounded blobs, but with much less dense, with many less points. So, but even if you look at the data set, we can see that there are points that are simply noise scattered around the data set. But in the top left, we see that there is some correlation between points. They are not there randomly. There are more than what you would expect. And if we try to use here HBScan with the parameters as before, we are not able to detect this cluster. But now you might even think, well, if we're not able to find this data set, to find this clustering with these parameters, we might simply change the parameters. So let's just lower the C. Let's see how it works if we would like to adjust the parameters to find more clusters. And if we do this, so like we decrease the epsilon and the minimum number of samples, this is the result. This is not what we aimed before when we try to find this cluster. So we can see that we can actually find 4 small clusters on the top left of our plot. This is something, this means that there is something there. The algorithm is able to detect something there, but it's not able to understand that those small clusters should be merged into a unique clusters. And what is even worse, I would say, is that the large blob to the right is still scattered, is still divided into more different, many other, I think 3 or 4 subclusters, and this is something that we don't want to see, because those subclusters, they clearly belong to the larger blob. But so now our question now is, how can this problem be solved? And if we think, we might already have at least a guess of a possible solution about this problem. If we think before about hierarchical clustering was exactly with the dendrogram, was showing how the different clusters were interconnected with each other. You could see a supercluster, a larger cluster, divided into many small clusters. And what we could do is using such information, such hierarchical structure, to understand whether many subclusters are a unique large cluster or not, or if instead we rather prefer having many subclusters. But this is something that we clearly we don't want to do this by looking at the dendrogram on a qualitative manner. We would like to have an algorithm that does this for us in an automatic way. And this is the next topic, the last algorithm, clustering algorithm we discussed today. That is HBScan. This is quite recent algorithm, and H stands for hierarchical. It somehow is an hierarchical extension of a density-based of HBScan. But it's not only about that. So HBScan is quite an old algorithm. It also see other different improvements. Let's start with the first improvement of HDBScan over DBScan. The first thing that HDBScan does is modifying the distance of the space. Is making a distortion, and instead of having our input distance, let's say an Euclidean distance, it uses a mutual reachability distance that is defined as you can see in the screen. So it's the maximum value between two chord distances. So the mutual reachability distance of 2 points A and B is the maximum of the chord distance, that is a specific distance specific of each point and the distance between the 2 points. Now let's see step by step what this means. Firstly, let's focus on the chord distance. What is this chord distance? You can see a parameter now that is k. This k has some value. Now we set it for understanding, just k equals 2, as it is here. And now we would like to see what is the chord distance of a point A that you can see now on the screen. Well, the chord distance for k equals 2 is the distance of the point A to the second closest point. As you can see in the screen, you have this red circle, and the radius is our chord distance. That just arrives, it just touches the center of the second closest distance. But then if we are looking at the chord distance of another particle, the A prime particle, that lies in a less dense region, it only has one neighbor next to it, well, the chord distance for k equals 2 is much larger value. So you see that it's arriving to the other cluster, because the second closest distance is into the other cluster of group of particles to the left. And if we are then computing the chord distance, the mutual reachability distance of all these particles, this is what we would find in the case in the case of the left. We have then the mutual reachability distance between A and B is equal to the distance of to the original distance between those two points. Well, this happens because A is located in a dense region, and as you can see, the mutual reachability distance is essentially the same for all those points that live in a very dense region. If we then instead would like to compute the mutual reachability distance between A prime and B prime, in the example to the right, we will find that even though those particles are pretty much the same distance of A and B, their mutual reachability distance is greatly increased, because then it becomes equal to the chord distance of A prime. So now I can show you a guess, because this is just a guess, of how the mutual reachability distance would be from the example that we have to the left. And this is what would happen. So we have, for the cluster to the left would almost remain unchanged, so their distance wouldn't change much, while the two other particles to the right would get very far apart for the effect of this mutual reachability distance with k equals 2. So the effect of using a mutual reachability distance is it facilitates the detection of noise, makes noise more evident. It avoids that points that are close to each other, but just few of them, a bunch of them, might by mistake be detected as a cluster. So you fix this k, and it avoids that this the cluster of with numbers smaller than k points would be labeled as a cluster. while instead we see it as noise. So now we are going to test on a quantitative manner HBScan on a real data set. But in this case, we are not directly testing it on the previous data set. And the reason is that there are several steps of this algorithm still, so I haven't explained everything clearly. And we would like to see how it acts on this real data set without necessarily guessing on a qualitative manner all the quantities. But still, this is a quite simplified data set compared to the previous one. There are not many particles, and we can understand, we can see how it works. The first thing that this algorithm does is building a minimum spanning tree. In this minimum spanning tree, edges between points are their mutual reachability distance. The way this minimum spanning tree is built deploys some graph theory techniques, and it is constructed as follows. So the idea is that removing any of the edges that you can see in the plot, it would make this graph that now is connected into a disconnected graph. So remove any of this edge, and then you would see that you cannot, the graph would split into two different components. And each removal would make a further split. What is even more interesting is that this is built in such a way that among all the possible combinations, the edge that you would remove for splitting the graph is the one with the lowest mutual reachability distance. So all the others have been with higher mutual reachability distance have been removed. So this means that when you're removing an edge, you are disconnecting the graph, and then you're sure that if all the other possible connection between the two now disconnected parts of the graph all have a distance that is larger than the edge you just removed. And you can see that the different mutual reachability distance values are have different colors that are given by the bar to the right. So you can see now how it works. So you have different colors. You can see you have different purple cluster, which are the lowest values, and then you can also see quite some more distant points which have like green or yellow colors. From this minimum spanning tree, then you can build a dendrogram that you already might remember from previous slides from the hierarchical clustering. In this dendrogram, you have some colors, but be aware that the colors that you have in the dendrogram are not the same on the minimum spanning tree. So you can also read it on the axis, because in the dendrogram the different colors are the number of points that contains that specific branch. So now you probably remember how the hierarchical tree works. In the top we have one unique cluster that contains all points. And then while decreasing the distance that you can see on the y-axis, so the color is the bar to the right, while decreasing the distance, you start disconnecting your the tree that the minimum spanning tree. So and then you can definitely see this, and then you start making always you start disconnecting to smaller cluster your tree. So now we can see a more specific example that could facilitate understanding what is happening. Let's say now that we select a distance that is equal to 2 in this case, and we can see on the bar color bar in the minimum spanning tree that all edges that have a distance smaller or equal than 2 have color purple or dark blue. And if we disconnect, we remove all edges which have other colors, so not necessarily this purple, but all the yellow, green and light blue edges, then we would remain only with 3 disconnected clusters that are the ones enlightened by the red dashed line. And if you look at the dendrogram, again the red line that is cutting this dendrogram, then you can find the 3 clusters, you can see them, which are there. And this is something that we have seen almost exactly in when it came for hierarchical clustering. We have seen with the Varda algorithm that we were selecting for different distances, and each distance would give a different clustering. But now we have something more. We have now noise detection, let's say, or at least now we have a method to make noise a bit more far away. But still, if we now decided to just cut our dendrogram at a certain position, we would obtain again something comparable results to HBScan. And the reason is essentially that then, like, we would fix our threshold, distance thresholds, we would fix the level of the sea, and then we would not be able to detect clusters with different density. What is doing this algorithm? What is doing more is understanding to which level lower or higher density clusters should be merged into a unique cluster. Let's make again a more specific example. So if we look at the dendrogram again, we have a cluster all to the left, a branch that is immediately separating, that is the one in the minimum spanning tree to the top. And then we have 2 smaller clusters, or slightly smaller clusters, that are in the bottom of our minimum spanning tree plot. And we can see them also in the dendrogram. You can see the 2 small clusters as blue, and their equivalent position, the dendrogram, still with blue. And then with orange, the larger supercluster, both in the dendrogram and in the minimum spanning tree. At this point, what the algorithm does is guessing whether it should have only one supercluster, only the orange supercluster, or if you rather select the 2 smaller subclusters. This is something that you can you might decide by looking at the graph, for example, but we might prefer an automatic way that this algorithm is finding. And this passes through the condensed tree. This uses the only parameter, at least the only relevant parameter of HBScan, which says that the minimum cluster size is, in this case, we give it a 4. So we say a cluster should be at least of 4 elements, which is also quite intuitive parameter to give. And so let's see what is the condensed tree. We can see the lambda value on the y-axis, and this lambda value is essentially just the inverse of the distance. So it again is going from top to the lambda value is increasing from top to bottom, and again we can see that this is just it is just an inverted dendrogram. So it is very similar. On top you have this light, this yellow large branch, and this represents in the beginning that when the distance is quite high, you only have one cluster, large cluster, with a very large number of points, and the number of points is given by the color, but also by the width of the branch. And then you decrease the lambda value until a certain point it might disconnect. So firstly, you might have some disconnection before, even like one point after the other. So you can see these branches are shrinking it is more evident for the one below, the yellow one, but still. So they start losing nodes. But only sometimes, only in some occasion, this condensed tree is going to split into different clusters, at least there. And this happens only if the two subclusters that are created while decreasing the distance are both larger than our minimum cluster size. Otherwise, they would just disappear. They would just be cancelled. If, for example, you have only one node, or even 2 or 3, because we put 4 as a minimal cluster size, nodes that are just removed from one cluster, well, in this case, you wouldn't see another branch rising from the tree. This happens only if the clusters are somehow bigger. So, like, we can see that at a certain point the first branch is going to split into 2 different branches, one to the left, and then the one to the right is immediately splitting into other more branches, and then the one in the center is finally splitting also into small branches. So you can see now we can count, and there are totally 7 of these clusters, and then they have a different hierarchical level. And you might want to find what are the clusters that actually are the ones more representative. So you might take the very first one that groups all particles together, or you might take all the smallest ones. So you have like the one to the left, the one to the right, and then the 2 small in the center. There will be 4 clusters. And HBScan decides what are the clusters that remain in a simple, rather straightforward way. That is just measuring the area of all those branches. So you have so the area is just one base. Essentially, could be is the initial width, and then you have the height. That is the time that this cluster survives before splitting. So it's not exactly a rectangle, as you can see, because the cluster shrink over while decreasing the distance. But then you can compute these areas, and then you can compare the sum of the area of all subclusters with the area of the initial supercluster. And then you can decide if the area is larger of the supercluster, you divide, you keep those, otherwise you keep the supercluster. And this is the final result, as you can imagine. So those 3 clusters have definitely a larger area than the yellow one on top. And then also the 2 small ones that are originating from the middle cluster are also quite small. They live pretty for a short time. They are also start being very small. So these 3 are the 3 clusters that we find, and this is the final results. Indeed, that's what we find, which is a reasonable result. Also because I actually generate this data set using 3 blobs, and this is exactly what we were looking for. And now we can come back on our initial dataset, and this is our final result. So we put minimum cluster size equals to 8, and then we find clusters of all our clusters that are 7 in this case. We are able to detect the different shapes, the half moons. We are able to detect the one to the top left that has a much lower density than the others. And I would say we are quite satisfied with the results. So we are obtaining what we were looking for. So now, with this algorithm, I'm gonna conclude this lecture about clustering. And well, what I would like to really point out is even though you might have seen this lecture as a continuous improvement in the quality of clustering. So we have one method, did not solve some problem, then we found another method, and this method did not solve another problem, then until we found the best solution, HBScan, that solves everything. This is not the message that I aim to give with this lecture. It is true, this is how it was structured, but all of these methods still have reason to exist and being used. So, for example, K-means is very good at finding compact clusters, it's extremely fast, and then it has many deployments. Hierarchical clustering is very useful for finding different hierarchies and of data sets that are somehow stable, so you don't have to make continuous analysis, and you want a simple, understandable analysis of this relationship. And then you have the density-based clustering that are good for different shapes. But still, what I can say is that if you're working on unknown data, this is something that now it is very important, because we have this huge availability of data. So imagine, even if you're going to the Nomad archive and then you're retrieving a data set with hundreds of thousands of data, and then you might want to find some clusters, you don't know much about the data. You might find difficult to define to define the number of clusters you want. You don't want to spend much time doing some fine tuning, and in this case, maybe at least the first algorithm I would pick is HBScan for this purpose. And indeed, you can also find such application on the AI toolkit, and then you will see in the next hands-on session an example of how this is used. But now, in these very last minutes, I would like to give a very brief overview about another topic that I won't have time to discuss in detail, but I just want to give a qualitative understanding of dimension reduction. This is also important. This is a very important topic, but here we are just treating it as a mean for visualizing data. Again, we have a very large data set that you might have retrieved from the Nomad archive, and then you want to analyze this highly multidimensional data set. And we have seen that it's important to visualize classes. We can understand better how they are interconnected, and it helps having a visualization. And so this is the reason why we use dimension reduction. We have many dimensions, and we are going to project this highly dimensional data set into a bending space that allows us to visualize it, so two-dimensional space in our specific situation. Also in a three-dimensional we might do it, but usually two-dimensional data sets are more understandable. So let's see some of these techniques. The point is that when you're doing this reduction, you also want to preserve information. So let's see how this can be done using different strategies. So I will just discuss two algorithms, and both on a very qualitative manner. One is PCA, Principal Component Analysis, that is a very well-known and widely used algorithm. And again, we are going to see how it would work on a dataset, artificial dataset that you can see now on the screen. We have these 7 particles on a two-dimensional space. And now, rather than finding clusters, we would like to project this dataset onto a one-dimensional embedding space. As a random guess, now we project this data onto the y-axis. And this is what we would obtain. So we would see all particles next to each other and next to the center. But this is something that we are not very happy about it, because if we look at the dataset in a two-dimensional space, we can immediately see that there are two different clusters. And if we look at this one-dimensional projection, we are losing that information completely. And we don't particularly like it. So this is not a good embedding. If instead we are projecting on the x-axis, we would preserve much of the information. Now we can see two different groups of particles, and then we could imagine those are the two clusters that were already present in the two-dimensional embedding. two-dimensional original space. So what is the reason why we prefer one embedding respect to the other? Well, the reason is that we preserve variance, essentially. Variance is how much, you probably already know, is how much the data are far, essentially, from the mean. And it is a measure of how disordered data is. So if we have not much variance, the mean is quite enough for describing most of the data set. If we instead variance, if there is much variance, there is much disorder. If we have disorder, we have information, and information is in fact what we aim to keep in our embedding space. We want to have an embedding that preserves information. And we have seen that this is something that we can do if we keep the variance of our dataset. So what principal component analysis, PCA, does is finding the axis onto which the projection would preserve most of the variance. This is the principal component. Here we find only one principal component, and then we might find two principal components, and these are this is the space where we are making our projection. Okay, we can see many things. What PCA is doing is essentially a linear transformation. So we take our dataset, we find this axis, and then we make a projection. This is very nice because this is deterministic and interpretable. We can also measure how much we are losing because of, well, these principal components are the eigenvectors of the covariance matrix, and their eigenvalues are a measure of how much of the variance is preserved. And well, this is also deterministic because once we have constructed this matrix, this projection, we can we always have the same results, and so we can repeat the experiment, and it is interpretable because we have a very rigorous mathematical frame. But there is a problem, and maybe that, okay, it is maybe too rigorous. The fact that it's linear, not too rigorous, let's say the fact that it's linear does not allow for finding nonlinearity. So if you have nested clusters, the fact that it is interpretable also is something that we like, but sometimes there are some again nested clusters that are somehow difficult to explain with a linear model. So let's see another approach that is, I would say, very different for all this to this extent. That is TSNE. Here we have again the same data sets, and what TSNE is doing is computing all pairwise distances of all particles, and based on these distances it would construct a matrix of joint probabilities. And this matrix says how much is likely that one point is close to another. So if two points are close to each other, then they are likely to be in proximity. And we would like to preserve these pairwise distances, these joint probabilities, as much as possible during the embedding. And the algorithm is the following. So we TSNE would first make a random projection of these points into an embedding space, and then in the embedding space would recompute all pairwise distances and likelihood, and would then try to optimize with a stochastic process all the relative distances in the embedding space, such that the distance, the KL divergence of the joint probabilities of in the original and the embedding space is minimized. So to make these probabilities as close as possible. So after a number of steps, you would finally find, after a stochastic random process, you would find some good placement of the particles. So we can see that this method is very much different from PCA because it is nonlinear. And this could be good because it allows for finding nonlinear interaction, nonlinear. So if we nonlinear interaction of the clusters and displacements. It is stochastic, but this is a problem because if we make the embedding and then we repeat the experiment, we are not necessarily able to find the same results. So it can find different minima, and we cannot reproduce it. And it's also not interpretable. So if we're not creating a model. So with PCA, when we have our embedding space, if we had another point, we could apply the same transformation and find the new find its position in the embedding space. For TSNE, that's not true. So it is an optimization that depends only on the specific data set. It cannot be applied on new data points. So this is everything about dimension reduction, everything I can explain in this very short time. I prefer giving these two methods, PCA, TSNE. I also would like to mention that dimension reduction is a very wide field, so it's very difficult to reduce all of this to only these two algorithms as much as for clustering, but this is particularly reductive. And but still, for us it's also important to have an idea of how this works and how important it is to deal with large data sets and when they have many dimensions, and that it is important to visualize our data points onto a two-dimensional surface. This was all, and thank you for the attention.